this with the robot?
Yeah, I did.
Really?
Yeah. Let me get like a...
How did you do it?
The laser pointer won't work.
Yeah, but I just take an advanced.
But you have this.
Oh, nice.
It's okay. It's okay to hit the screen.
Ah.
How hard?
Okay, maybe you should begin. Talk by Annabelle. It's adaptive quantum state tomography.
Okay, so
It's about half an hour, but let's say that will finish like 25 minutes or before.
sure, yeah.
So that, but ask questions.
Yeah, feel free to ask questions at any time. Okay.
Go.
Okay, so yes. Okay, so I hope everything works now. I decided today to talk about not Fermi-Howard stuff for a change. I hope you all appreciate that. And instead, I want to talk about quantum state tomography and in particular, how to make it adaptive during the measurement process. Okay, so the main motivation. Let's start with this. Okay, so these are the people involved in this work, and I should mention in particular Hannah, who did a lot of the actual work here. So the main motivation is, of course, that we have a lot of quantum data available, in particular from quantum simulation experiments, which is, of course, a great motivation for me, but also from more and more from quantum computation platforms. And one question that you need to ask in this context is, how do you certify that you prepare the state that you want to prepare? Or if you look at some complicated quantum many-body system, more from the perspective of quantum simulation, how do you probe the state and how do you characterize the state? And one way is to do full state tomography. And the idea there is that you, okay, so you prepare your complicated quantum state. It looks horrible. So this is, for example, the quantum gas spectrometer setup from Annabelle Bohrdt in Munich. I find it very scary, so I will be very small now. But what comes out of this are beautiful pictures. And so what you do is you project measurements of your quantum system. And that's the measurement in one way or another that all of those devices provide you with. And there is, of course, a lot of information contained in those images. So what you're seeing here is really, this is I promise not to talk about Fermi-Howard. This is, of course, Fermi-Howard snapshot. So what you're seeing here is a realization of Fermi-Howard model where you have lithium atoms in an optical lattice, and you actually do a projective measurement where you have a quantum state and see where each of these atoms is sitting. And so to make this video even more clear, so what I can only imagine that is so fascinating about this picture is that in your experiment you realize a quantum state which can be a superposition of many different configurations. And I draw, it doesn't really matter what I draw here, but it's like some superposition that you have realized, and I try to use the pointer, but I can't. But then when you average over all of those, what you will get is just some blob. And now, if you have projective measurements, which you have in actually most of the quantum simulation and computation platforms in one way or the other, then in each measurement you actually obtain a snapshot like this or a snapshot like that, and so on. So from that, to begin with, you have a lot more information available. But so this is something that I keep telling you about, and I keep telling you how like this is motivated by looking for specific patterns or snapshots and so on and so on. So I've talked about this a lot. But now I kind of start something under the rock here, which is that in principle you also have phase information. And even in the simplest case where you have like a spin singlet, you kind of have phase information whether you have like a minus. I use this big stick here. Whether you have a minus or here. Wow. And this kind of information, I mean, here it's just plus and minus, but in principle it could also be a complex phase. And this kind of information you don't get from these projective measurements in one basis. So in particular, let's go through the example for two spins, so two qubits, whatever is your language. So you have a state that looks something like this, right? So you have your not in your sigma 1. They come with an amplitude, but they also come with a phase. Now, in this typical measurement that we do, when we always measure in the Z basis, or for example, from the habitation order, we always measure in the fog basis. Here, basically what you measure is this probability distribution. So you basically measure the absolute value squared, which basically gives you this probability here. So this gives you those p's here. But it doesn't give you any information about these complex spaces here. So to learn something about the complex spaces, you actually need to measure in different bases. So here, for example, if you apply a gate here, such that you measure the x basis on your first and in the z basis on your second, would give you the possibility to obtain this phase difference here. And of course, now you can go through all the different combinations that you have here to obtain all the phases that you need here to reconstruct your quantum state fully. Now, if you do that brute force, there's a lot of combinations to go through, right? So if you just say, I'm going to take my system, whatever it is, and go through all the possible basis configurations, this will be a lot of effort. And I should also mention that it's kind of even worse than that, right? Because say you start from this XXX configuration, what you do is you really measure snapshots. So doing one measurement is not enough. One measurement in the XXX basis, but this does not give you the expectation value, but it just gives you one projected measurement. So in principle, even for this one basis configurations, you need to do a lot of measurements to really have the expectation value, and then you need to go through all different combinations. So that's kind of a mess. And this is something that people do for like 2 or 3 or maybe 4 spins of qubits, but beyond that, it's basically completely infeasible to do. Now, the main idea in this talk now is to use active learning. So the idea is that you start from some measurement configuration, chosen one way or the other, could be random, so you start from some very small initial data set, and based on the knowledge that you already have about your state from that first initial measurements, you propose which measurement basis you should measure next to have the most information gained. So basically, the point is that you, as soon as you take any measurements of the system, you have some information about the state. And that means not all of these basis configurations will have the same information content for the particular quantum state at hand. And therefore, if we start to basically look for which basis configuration will give us the most information, given that we already know something about the state, we hopefully can greatly reduce the number of overall configurations that we need. Okay. So in this particular work, and also the general ideas was more general, but in this particular work, we used restricted Boltzmann machines, or RBMs, to reconstruct the state. And so I basically want to spend one slide explaining how these RBMs work for state reconstruction. And there is a lot of work, in particular by the group of quantum mechanical performed by Giacomo Tollai, and there is like a review article also on like how this general framework of these Boltzmann machines works. Okay, so the general idea is that you have some quantum state and you want to reconstruct it. And for that, you need to use some representation. So what we're using are these restricted Boltzmann machines, which look like something like this. In principle, you just need something where you can represent your quantum state with. So people, for example, also use matrix product states for that, or there's a whole line of work on using different neural network architectures. So there is things to say, for example, use recurrent neural networks for this, or convolutional neural networks, and so on. There's a whole zoo of representations that you can choose for your state. And these RBMs are kind of the simplest ones, so that's kind of the motivation to use them. And so the restricted Boltzmann machine basically consists of these 2 layers here. So you have the visible layer and the hidden layer. The visible layer basically is your spin configuration that you see. And the hidden layer, well, is the hidden layer now. It's restricted because there are no connections within the layer, but just between the 2 layers. And what we basically do is we have 2 of those. So I only draw one, but we actually have 2. One for the amplitude and one for the phase. So there is also different ways one can go about this. In principle, you could also just use one and have it be complex, but it turns out for practical purposes that it's kind of the best for the training process to have 2 separate networks for amplitude and phase. And so, but basically what we want to do now is we have these like little indices here, these lambdas and these mu's. These stand for the network parameters. So that's basically weights of these lines that I'm drawing here. And what we want to do is we want to learn those network parameters such that this learned quantum state here, this psi lambda min of x, is as close as possible to our actual quantum state that we have realized here. And what we do to the actual learn this quantum state is basically we train a restricted quantum machine on a data set of measurements. And these measurements, according now, are just quantum projective measurements. So we don't need the expectation value of a polygon or like whatever you have there, but you really use those snapshots that you naturally get from the experiment as input here. And also what's indicated here already is that we need those measurements in a set of bases B, and that's kind of what we're trying to optimize over. So that's kind of the general idea how this will work. So you have a training set of data that you took, for example, from the experiment or numerically, and then you train this network by optimizing these parameters lambda in one network and mu in the other network to basically get this state that you reconstructed here as close as possible to the state that your data is coming from. Okay, and this has actually already been used successfully with the group of Michel Lukin. So this is work by Giacomo Tolle from, I think, 3 years ago by now, and they basically reconstructed a state from this Rydberg tweezer atom array using a restricted Boltzmann machine. They actually included an additional noise layer to accommodate experimental noise sources and so on. But the main point was that they really used a restricted Boltzmann machine to reconstruct the quantum state of the experiment. And from this reconstruction, then they could actually, how should I say, from the reconstruction, they could reconstruct observables that were not straightforward to obtain from the experimental data directly. So this is, for example, showing I think the second Rényi entropy. That's something that you would have a hard time to directly get out of the measured data, but they got it from their reconstruction. I think I don't know which, I think the red one is like a numerical simulation of the system, and the blue dots is their reconstruction of this quantity from their reconstruction from the experimental data. So you see that it agrees nicely. But the main point in this work is that actually for this particular system, so it was a 1D chain of those Rydberg atoms with I think 8 atoms in them, is that it's basically a positive value wave function. So basically the ground state of the system can be written in this way. And now you already see what I kind of talked about earlier, there is no phase information here. So basically all the information about the ground state of the system that they were looking at, and then they reconstructed with this Boltzmann machine, was already contained in just taking snapshots in their normal measurement basis, which is very nice for them. But in general, this is not the case. And in particular, you need to have some prior knowledge about your system to even know that this is true, right? So if I give you some quantum state and you know nothing about it, then you have no chance of knowing whether this is true. So in principle, in general, you will always need to reconstruct a phase too. Okay, so basically what they did is, in a way, they did passive.
Phase was hidden. Phase information was hidden. What was this process then?
So basically, they measured, so I mean, they run the experiment, they measure configurations X with a certain probability P of X. And they basically, I mean, the only thing that they basically do is use the restricted Boltzmann machine as a good, like function that has a lot of representative power to approximate this probability distribution here from few measurements. So they kind of take rather few measurements and then they do a good job at approximating the full probability distribution here. And that's the main point. So in principle, in this kind of experiment, you only have the P of X, which kind of makes it a lot easier. So in principle, if you take a lot of samples, then you already know your probability distribution because it's literally the probability of getting a given sample. And in this particular case, I think they took a lot less data than they would have needed to do it brute forcefully. So it's like a good way of interpolating basically in this space. And then once, I mean, you do not necessarily have to do this with a restricted Boltzmann machine. They kind of showed that it's an efficient way to do it, but you need very little data. And then once you have some state representation, then of course from that state representation, you can extract all sorts of quantities, right? So once you have like some reconstruction of your quantum state, then you can go and just literally calculate something like the Rényi entropy and stuff like that.
So why is there no phase information? Is that because there are no super externals?
Yeah, I don't remember exactly. So I think they go to a particular phase, and I think they go to the C2 phase or something like that. And then the ground state is something where you just have like the equal superposition, and then it's but yeah. So I think this is a very nice example to show that these restricted Boltzmann machines are a good way of representing this probability distribution. But this is a very peculiar system, kind of, that you cannot in general assume of your quantum system. The S in the inset, I don't remember exactly, but I think it must be maybe. So I mean, it was. Yeah, I don't remember exactly where. Yeah, I mean, it's like it's in this paper. It's a nice paper overall. They did like some nice work at like modeling noise and everything. Okay. So, but wait, what they did really is kind of this passive learning. So they basically they took a data set of experimental measurements, so that's what in this box, and then they trained their network to learn from that set of data. And what we want to do is active learning, where instead of having this box of measurements to begin with, that our agent, or like this little robot guy here, can ask for specific measurement configurations. So the idea is now that our agent basically itself can tell us which measurement configuration would be most informative. And this is something that has been, so this general active learning idea is somewhat old. One example where people use this, where it came up at this point like 17 years ago, is in like recognizing speech, because it's like an example where it's kind of expensive to get data points, right? Because so what you want to do is you want to train a machine to recognize the speech, what I'm saying. So basically there is like a recording of my voice, and then the label for that recording would be the transcript of what I actually said. And then you train a machine to recognize, basically to get this information out of the recording of my voice alone. So you kind of need label training data for that. But getting a lot of label training data is very expensive, because you need to have some human being who sits there and types what I'm saying, right? So you kind of want to reduce the overall amount of those examples that you have. And therefore, that's where people use this active learning idea, because they basically started to train a machine with a given data set of voice recordings and transcripts of those voice recordings. And then they let the machine itself decide for which. So, I mean, it's easy to get voice recordings, right? That's kind of the cheap part. But it's hard to get the transcripts of those voice recordings, because we actually need to have humans sitting there and listen to the voice recordings and type them down. So they basically let the machine decide for which voice recordings it would be most informative to get transcripts, to get better at speech recognition in general. So that's kind of the general idea of this active learning framework. And now we, of course, don't want to do speech recognition. We don't want to work in some call center or whatever. What we want to do is state tomography. And there we basically have now a two-stage process. So for this RBM state reconstruction, what I didn't mention earlier, but it's kind of clear when you look at it for a second, is that you kind of have one measurement basis, which is like the reference basis. So it's kind of preferred over the others, because that's the one in which you will measure the amplitude. So as a first step, you need to determine which measurement basis will be this reference basis. And then in a second, so that's kind of what we want to do first. And then in the second step, you want to take measurements in different measurement configurations. So basically, as a first step now, we do a small set of global bases. And then we train an ensemble of RBMs on that. So the general idea is always to train an ensemble. So to have like n RBMs, could be 5, could be 10, something on that order of magnitude. And then ask in which, so we do repeat this for a small set of global bases. For example, one would be like all in X, all in Y, all in Z. That would be one example. Of course, you can also do like some other rotation, but just a small set of those to choose which one should be our reference basis. And then we ask, so we do a query by committee. That's why we kind of train a committee of RBMs. We ask which of those bases that we consider has the smallest variance between the RBMs. So we basically have our ensemble, and we basically ask in which reference basis. So this is important, because this is kind of where we will get our amplitudes from. So which reference basis will lead to the smallest variance? So in which measurement basis do they agree most? And that's what we choose as the reference basis.
Sorry, Annabelle, let me ask you something. So all of these machinery now refers essentially to stationary configurations, or you can model also dynamical situations?
I mean, if you have dynamics, you would want to repeat this in every time step, because you basically want to, you want to reconstruct one quantum state, right? And if it has some dynamics, I mean, that's like a super interesting question, but like that basically adds like another dimension to it. So right now it would be like one, you could of course repeat the same thing in time. I could actually also imagine that if you have some dynamics, like process that you can profit a lot from knowing like the time step beforehand to then be more efficient in the next one. But yeah, so this is all for like a static situation. Okay, so with that, we fix our reference basis. And then we of course need to, that's what I like mentioned earlier, where you could do like a brute force approach. Now we need to measure in a lot of different other bases to figure out what the phase of our quantum state is. And in this case, we again do a query by committee, but now we kind of want to figure out, so we fixed our reference basis, and now we want to figure out where do we need more information? So where is the variance highest? Because that's kind of the place where the RBMs disagree most, will be where the most confusion is within our committee. And that will be where we need to take more measurements to solve that confusion and to find out the details about our state. So that's basically the second step. And from that, we then basically loop as long as you want. So either until we have reached a certain accuracy or until our experimental friends or whoever says, I won't take any measurements anymore. So that's the cutoffs that you can choose here. Okay, so let's look at an example. So here we are looking at a GHZ state with 9 qubits. So this is the training epoch. So basically this is the number of samples as a function of the training epoch. So we keep adding samples here. And what is plotted up here is the Kullback-Leibler divergence. So that is basically what we are minimizing when we train the RBMs. So that's basically just tells us how different is the learned distribution from the input distribution. And okay, now the green line here is the baseline. So that is what happens if we take the same number of measurement configurations, the same number of samples, but we choose the measurement configurations randomly. The blue lines is the active learning. So that basically is telling us we do a fixed set of measurement configurations, but for the active learning, the active learner chooses them. So that's kind of the most informative measurement configurations that we have. So we basically want to see whether it's better to do the blue thing where we do an informed choice of measurement configurations versus the green line where we just choose them randomly. And so what you're looking at here is the Kullback-Leibler divergence, which is actually the wrong quantity to answer that question, because the Kullback-Leibler divergence only tells you how well do I approximate the measured distribution with my reconstructed distribution. So given the fact that I'm looking at 2 different measured distributions, because in one case, the active learner determines which bases I'm measuring in the other case, I choose the measuring configurations randomly. So this only tells us how well the training of the RBMs worked. It doesn't tell us how well we chose the basis configurations. But it's of course an important quantity because that's what we're minimizing when we train those RBMs. So it's important to look at that too. And what you see is that in the end, they basically reach very similar values. So we want to minimize that. The active learner is slowly below, like slightly below that, but it's kind of in a similar ballpark. You might be wondering what this funky structure here is. That's due to the fact that whenever there is a step in the number of samples, we add more samples and then we start our training from 0 again. So you could also take other different approaches to that, but that's what we did here. And that means that so we basically reinitialize our RBMs to 0. So that means that first the Kullback-Leibler divergence will shoot up again, and then it will go down as we continue the training here. Okay, so what we learned from this is that the training of the RBMs in general works nice. Yeah.
You can also look at the Fisher information, right?
Yeah.
So this is like an estimation problem.
Yeah.
You're trying to find the.
Yeah. Yeah.
Is there any more information coming from Fisher information if you guys check it? Or...
Yeah, we haven't checked it. Actually, that's something that I also wanted to look into. So we kind of used the Kullback-Leibler divergence, like we looked at it because that's what's the most efficient to use for this training part. But yeah, it would actually be interesting to look at the Fisher information library. Yeah.
You have an idea also why around 4,000 epochs you have this maximum of the Kullback-Leibler?
Like this one here? I mean, this, like basically these like spikes up they are kind of random to some extent because you basically like you initialize from new, so you basically didn't do any training at all. Like whenever you have a step here, you basically start from new here, and then it's just a question of what the data that you have in your pool right now looks like. So yeah, I mean, it's not. I mean, it's a good question because it's not completely true that this doesn't contain any information, because this height basically tells you how different it tells you something about your data set, right? It doesn't tell you anything about the training process or reconstruction, but it tells you something about like what your data looks like. That basically the random initialization looks very bad for just data, but that's all.
So this divergence point is 0.
So here is 0.
Also 0.
Yeah, that's because I cut off this part. Yeah, I did a bad job here. Right, so because what we all actually want to look at in this case, what we know that we prepared a GHC state is that we can directly look at the fidelity. So we basically know which state we prepared. I mean, this is like a numerics experiment. There is no noise or whatever. So we know which state we prepared, so we can check how close we are to reconstructing the state that we're looking at. And now again, we have this green baseline. Also this doesn't change over the epochs because we just used the last point and plotted to make the plot more crowded than it is. So this is basically, this baseline is the best you can get for those random basis configurations. And the blue is again our active learners. So the different blue lines here is basically our ensemble of RBMs that we are training. And what you see is, again, you see those spikes up. So this is 1 minus the fidelity. So we want to minimize this quantity again. You see those spikes up whenever we add new training data for the same reason as before, because we start initializing from a random configuration, but then you see that during the training it goes down. And what you also see is that in the end, we end up with a much better fidelity than as if we had chosen our measurement configurations at random. And that's kind of what we want to achieve. So we can also look at this for different system sizes. So we looked at the 9 qubit situation before, we can look at 5, 7, 15, and in all those cases, we find basically two things. We find that the fidelity is much better for the active learner. So it's always better to do an informed choice of your measurement configurations than to choose them randomly. And the other thing is that here we're looking at the variance. So this is basically how different the fidelity is within our ensemble of RBMs. And what you see is that for the baseline, this can be quite large. Whereas for the active learner, it's much smaller, which means that if you have these kind of informative basis configurations, then you get a better reconstruction and you get a good reconstruction with a higher probability. So basically, there's much less variance. So if you do the same thing over and over again, you will always get a very similar state in reconstruction, which is also something that's kind of nice. And we can also do the same thing for, of course, different states. So here we, for example, looked at a state with 5 qubits, where all configurations have the same probability, or where all spins are pointing up. So this is kind of trivial here. There, in this case, like both perform very well because it's very easy to just measure in the Z basis and get a lot of information from that. Okay, and so I think I'm already kind of over time, but let me very briefly mention this. So this was kind of like a quantum info perspective where you look at GHC states and those kinds of states. I also talked a lot about quantum simulation in the beginning. One example that we looked at are these kinetically constrained spin chains. So due to lack of time, I don't want to go into any details, but it's kind of like a spin Hamiltonian where you have like Sx is C as X terms. So it's kind of a bit of a complicated Hamiltonian. And we look at the ground state of this Hamiltonian and try to reconstruct it for a system with 19 sites in this case. And now in this case, it's not so easy anymore to look at the fidelity, right? Because we cannot just take the actual state and calculate the overlap. So that's something that becomes harder and harder as you go to larger systems, and at some point it becomes impossible because you just cannot do the exact state that you're trying to reconstruct anymore. So what instead we're looking at now is observables from the system. And one is the local density. So that's basically, yeah, it's just like defined as this. It doesn't really matter, but what you see is the target state, so the actual ground state has this modulation here. And that's something that's very well reproduced by the active learner. So you see really very well capture these oscillations in the density here, whereas the baseline basically completely fails to capture them. And it's kind of a, so it's a very nice physical feature that you see that comes out of this active learning. And then there is also more complicated correlators that we looked at those because they have a combination of SX, SZ, and SX in them. So it kind of suggests that you need to look at different basis configurations to reconstruct them well. And there we also find that, again, this black line is the target state, so the state that we are sampling from, that we do our measurements on, and the blue line is the active learner. And you see that there is some structure that's captured overall pretty well. Also, the overall magnitude is captured pretty well, whereas the baseline is kind of significantly below that. So, yeah.
So is it possible to realize this kind of 3-spin interaction in any of the quantum simulators?
Yeah, I mean, in principle, this is similar to these like PXP models, right? That you would do like that, and I thought a lot of people thought about it as Rydberg atom context, where you have like a concave, and then that gives you like this projection. Because the main point of this term is basically that you flip a spin, but only if there is a like, yeah. And so that's one way. There is also this. You can map this to some left gauge theory model, and there's also people thinking about realizing this with like superconducting qubits and stuff. So there are, in general, ways to realize it. It's perhaps not as straightforward as like, I don't know, like.
And that's why you're calling it kinetically constrained, because of
because you can only do the flip if you have
So it's an effect even if don't.
Yeah. It's an effect. Like it's not a microscopic constraint. Yes, exactly. Yeah. But so the main motivation was to look at something where we would hope that one needs different basis configurations to reconstruct quantities of interest that just correlated. And so the overall kind of conclusion here is that really, independently of what states we looked at, we did a significantly better job if we do this active learning procedure where we take highly informative measurements instead of just randomly sampling over the space. And so I think now I'm like 10 minutes over time, but let me thank you for your attention. We collaborate.
One last question. With the active learners, you would expect a smaller error.
Yeah, in general, I don't know. So I actually didn't expect this to happen, and I was surprised when we saw. Like, I was positively surprised to see it. I'm not sure if this is something that you in general can expect. So intuitively, I think it makes sense because you do the most informative measurements, so you have the most knowledge about your state. So you kind of, like you basically get peaks, like you get high peaks as opposed to measuring in basis configurations where you get some flat distribution. So I think it intuitively makes sense, but I'm not sure if it's always true for these kind of active learning systems.
Is there any order?
So not really. So these are like, here on the left are the theorists, and then here is like Immanuel Bloch's group, and then here is Markus Steiner's group, but then within the theorists, it's kind of randomly ordered. And I hope we don't forget people. So this is Hannah, who did like a lot of the actual work, and Fabian, who like did a lot of consulting on this constraint spin chain model.
Good. Thank you very much. So, Jaren? Yes.